staying post, startups on the grind, chasing their dreams in the realm of innovation. Nothing's as it seems, networking sessions where minds collide. Ideas sparking innovation as our guide. From the product launch to thought leadership stance, we're carving our path, taking every change. So let's raise our voices in this digital century. Tech giants and startups rewriting history. In the pursuit of innovation, we stand tall. At COMPUTEX is embrace when dreams evolve. Innovation spark, illuminate digital nights. Yes, yes, yes. Tech titans, startups, forging paths ahead. Let's go. At COMPUTEX core, where legends are bred, where legends are bred. AI nights. Hey. Innovation spark, illuminate digital nights. Yes, yes, yes. Tech titans, startups, forging paths ahead. Let's go. At COMPUTEX core, where legends are bred, where legends are bred. Check it, it's the rise of the tech scene. Listen close, AI's the heartbeat. Tech giants, they impose startups on the grind, chasing their dreams in the realm of innovation. Nothing's as it seems, networking sessions where minds collide. Ideas sparking innovation as our guide. From the product launch to thought leadership stance, we're carving our path, taking every change. So let's raise our voices in this digital century. Tech giants and startups rewriting history. In the pursuit of innovation, we stand tall. At COMPUTEX is embrace when dreams evolve. Innovation spark, illuminate digital nights. Yes, yes, yes. Tech titans, startups, forging paths ahead. Let's go. At COMPUTEX core, where legends are bred, where legends are bred.
Ladies and gentlemen, please welcome Chairman of TITRA, James Huang.
Good morning, ladies and gentlemen. Welcome to COMPUTEX CEO Keynote. On behalf of COMPUTEX, I'm thrilled to introduce our keynote speaker, Dr. Zhike Che, Director General of Delta Research Center at Delta Electronics. Delta is a leader in power electronics and automation, and the company is driving AI-powered advancement. AI is transforming every industry, and automation is no exception. Challenges that used to bottleneck traditional systems can now be tackled by new innovations developed by AI tools. Delta is at the forefront of utilizing AI to create next-gen solutions, guided by Dr. Chair's visionary leadership. Dr. Chair is a distinguished expert in AI and automation, with an extensive portfolio of published research in AI. Today, Dr. Chair will share insights on the latest trends and Delta's cutting-edge solutions, along with his vision for the future of AI in industrial and building automation. So, ladies and gentlemen, please join me in welcoming Dr. Chair to the stage.
Hi.
Thank you, Dr.
Thank you.
Chair. Thank you.
That's it. Hi, everybody. It's a great honor to be able to give a technical talk in this forum during the height of AI revolution. The development of modern AI technology in the last 15 years is reminiscent of the development of modern physics in the beginning of last century. Imagine the boiling excitement and the enormous amount of incredible talents and intellectual efforts that went into it, and the relentless progress and the continuous flow of game-changing results one after another, and so on. Of course, the poster child of this development is the announcement of ChatGPT in November 2022 that truly stunned the world and triggers a worldwide race for large language model development, which in turn stimulates a strong wave of building up AI computing infrastructure. And that's why you see this almost insatiable demand for high-performance AI accelerators at an astonishing 35% CAGR, all right? So that's like the driving of today's AI industry. But to host these AI accelerators, we need a modern data center, which consists of a white space, which houses the IT equipment, including server, storage, network switch, as well as a gray space, which consists of a power delivery network and a thermal management network. One characteristic of this AI accelerator is they are very, very power hungry. For example, NVIDIA's A100 consumes about 400 watt. Its H100, 700 watt. Its B100, 1200 watt. And the latest GB200, about 2700 watt. It's almost like a rack of traditional CPU servers. So that's an enormous amount of power required. That's why we need an efficient power delivery network to service the energy needs of these AI accelerators. The job of a power delivery network is this. It's supposed to convert the electric energy coming from the electric grid, typically at the voltage level of 10K to 30K volts. Now, you're supposed to convert that into something like 1 volt, and then deliver them to various electric loads inside the data center in a way that minimizes the energy loss along the wire. That's the mission of a power delivery network. There are several power delivery network architectures that are currently in use. Delta has been working with all major cloud service providers in the world to design and develop essential building blocks for these architectures, including something like solid-state transformer, for example. Now, one trick to minimize the energy loss in the power delivery network is to maintain the voltage level high so as to minimize the amount of current traveling on the wire. That's the main trick. But this trick breaks down for the last lap power delivery. When you need to deliver this power to, for example, AI accelerators. Let's take an AI accelerator that consumes something like 2,000 watt and operating at the 0.5 volt. Then you need a current of 4,000 ampere to feed it. That's like a humongous amount of current. And that's why the latest solution to deliver power to this power-hungry AI accelerator is to deliver power vertically from the bottom of the AI accelerator chip to the chip itself. It's a vertical power delivery. By doing something like this, we can reduce the length of the last lap power delivery trace and accordingly cuts down the voltage drop and the energy loss, leading to something like 13% efficiency improvement, which may seem small, but is a major deal, But to be able, the key building block to do this vertical power delivery at the last lap is to be able to embed the power conversion mechanism inside the substrate, including its magnetic components. And that's the key enabling technology. Now, let's switch gear a little bit. Once the per accelerator power consumption exceeds 1,000 watt, then traditional air cooling is no longer sufficient. You are going to need something like liquid cooling. There are currently 3 types of liquid cooling on the market. One is air-to-liquid cooling, as exemplified by this air-assisted liquid cooling, AALC. This can reduce the power usage effectiveness, PUE, to something like 1.3. All right, so that's the first type. The second type is liquid-to-liquid cooling, as embodied by something called coolant distribution unit, which can reduce the PUE down to 1.1. But of course, the ultimate form of liquid cooling is immersion cooling, where you immerse the entire IT equipment in a pool of coolants. This can reduce the PUE further down to something like 1.03. At this point, Delta Electronics has a liquid cooling solution in all 3 categories. Its liquid-to-liquid coolant distribution unit in particular fashions several unique features. One is it's a highly efficient coolant pump, and it's a unique coolant transport pipe design that enables uniform flow rate inside the pipe. And it's a volume-efficient heat exchanger and improved system-level robustness through fault-tolerant design and rapid repair mechanism. We are also working on an end-to-end precision cooling solution for the entire data center. So it's not just a single component. We are also working on an end-to-end solution for data center cooling. So it is well known that Delta has been playing an essential role in supporting the non-IT part of modern AI data center. Everybody more or less knows that. It is less known that Delta also leverages modern AI technology to develop various innovative solutions for the market segment that it competes in, including wireless communication, industrial automation, building automation, and smart mobility. For the rest of this presentation, I'm going to talk about 3 such AI solutions. So the first step is to repurpose Wi-Fi, which was originally designed as a communication technology. Now we want to turn it into a sensor technology. So today we can actually leverage Wi-Fi signals to accurately position individual Wi-Fi devices. So how does that work? When an RF signal comes from a Wi-Fi device that reaches a Wi-Fi access point, the access point can compute the time of flight, the angle of arrival for that signal. And then by triangulation, we collect information and correlate them around neighboring access point. And collectively, we can pinpoint the location of the Wi-Fi device that emits the signal. So that's like in theory, that can be done. But the hard part is the so-called multi-pass problem. So what is it? Like when a signal coming from a Wi-Fi device reaches a Wi-Fi access point, the access point doesn't know the signal comes from the device directly all the signal gets bounced off some intermediate reflector and reaches the access point indirectly. This is a so-called multipass problem. We use AI algorithms to solve this multipass problem and come up with a precise positioning system whose error is about 35 centimeter, 0.35 meter, which is about 5 to 10 times smaller than existing signal strength-based Wi-Fi positioning system. So that's one instance. The second instance is that we can also use this Wi-Fi signal to measure vital signs. So what kind of vital signs? Like heart beating rate, breathing rate, and some sort of body movement that we can measure using Wi-Fi signals. So how does this part work? Turns out that the channel state information in modern Wi-Fi technology is very sensitive to minor geometrical changes in the surrounding environment, including something like a chest movement due to breathing or due to heart beating. These minor geometrical changes, the Wi-Fi signal can show the different variations. So by analyzing the minor variations in the Wi-Fi in the CSI of the Wi-Fi signals, we come up with a breathing rate estimation algorithm that can achieve something like 95% accuracy at a 5-meter distance, as well as a heart beating rate estimation algorithm that can achieve something like 83% accuracy at a 1-meter distance. So why is there a difference between these two? That's because the chest movement due to breathing is much bigger than the chest movement due to heart beating. In other words, it's easier to estimate the breathing rate than to estimate the heart beating rate. Right? So in this video, I'm going to show you the accuracy of this Wi-Fi-based breathing rate estimation algorithm. So we ask 2 test subjects to lie close to each other on the same bed. And then we ask each subject to put his smartphone on the side, turn on the Wi-Fi, and sleep on the bed and breathe at a particular rate. One guy at 10 beats per minute, the other guy at 15 beats per minute. And during the test, we also ask the test subject to change their posture. So for example, they can sleep on their back, they can sleep on their stomach facing down, or they can sleep on the side. And turns out that the result, then we use this breathing rate algorithm implemented in a Wi-Fi AP to measure their breathing rate. And the results are shown there on the screen. And it turns out that the resulting accuracy is more than 95% most of the time, even when these 2 people are pretty close to each other, meaning there's no interference. And also, the accuracy remains the same regardless of their sleep posture. This is really surprising. It means that our algorithm is able to pick up the minor change in the chest movement, even when the test subjects are facing down. Right? If you are lying like that, it's conceivable. It can be done. But when you lie facing down, it is also achievable. Then that's a somewhat surprise. Right? By combining the estimates of the breathing rate and the body movement function, we can do even better by predicting with 82% accuracy the sleep stage during a person's sleep. That is, we are able to tell when you sleep during the night whether you are in the wake stage, rapid eye movement, REM stage, light sleep stage, or deep sleep stage. We can even predict this sleep stage without using EEG. That's the key. It used to be the case that you can only rely on EEG equipment to do this kind of thing. Now, all you have to do is just put your Wi-Fi, your smartphone on your side, and we can predict your sleep stage with this level of accuracy. Because this algorithm does not require EEG, it enables so-called target memory consolidation during our day-to-day lives. That is, it makes it possible to enforce selective types of memory for a normal person while they sleep on a regular basis. When you go to bed and you want to reinforce certain types of memory, we can do that because we can predict when you are in a sleep stage. All right, that's what it means. So with this Wi-Fi sensor technology, it actually has many applications. So for example, we can use it for simple things like personal smartphone locationing. We can also use it for intrusion detection when nobody is supposed to be at home. We can support comprehensive sleep quality monitoring in a nursing home, for example, without using any wearable or smart bed sensor, just your smartphone, just the normal access point, and we can do that. And finally, we can support child presence detection, which is a new vehicle safety standard coming from the EU that requires every vehicle owner to be able to detect within 1 minute after leaving the vehicle whether there is a child or pet accidentally left in the vehicle. That's a new standard called child presence detection, and our Wi-Fi sensing technology can easily address this problem. We also apply this Wi-Fi sensor technology to something we call Q-Wi-Fi, Quality of Service Conscious Wi-Fi System, whose objective is to prove that a Wi-Fi system can achieve the same level of performance as a private 5G communication system at a much lower cost. So that's like a big if, and this is something that we want to prove. So towards that objective, we use AI algorithm to automate network-wide coordination among the access points and supporting self-organizing and self-optimizing mechanism. Q-Wi-Fi builds this device positioning capability as a first-class functionality into every constituent access point and is able to reduce the inter-AP handover latency from what used to be something like 100 to 150 milliseconds down to something like less than 30 milliseconds, which is comparable to or better than most 5G systems. And in addition, with the device positioning technology can enable more effective dynamic load balancing among Wi-Fi access points and continuous network operation even in the presence of planned or unplanned access point shutdown. So that's like what this Wi-Fi communication technology, once it turns into a sensor, then can be so many interesting applications. The second example is BIDS BIT, which aims to automate the process of applying drone to inspecting a large-scale infrastructure, such as a bridge, on an end-to-end basis. So what does that mean? This is what's involved today in inspecting a bridge without drone. The process is labor-intensive, time-consuming, error-prone, and dangerous. The quality of the inspection result is not particularly high. That's why people already try to use drone to help inspecting a bridge. That idea is not a new idea, so a lot of people are trying to do that. But the current practice still involves a large number of manual steps, which our BIT system aims to automate away. So that's the new thing, that we want to automate these previously manual steps. So what are these steps? When you are given a target bridge segment to be inspected, let's say you want to inspect a particular bridge segment, you need to first create a 3D model for it so that you can compute the inspection flight path for a drone and you can present the final inspection result. So you need a 3D model. And then you're going to compute that flight path for inspection. And that flight path better covers all the what we call inspection elements on the bridge. By inspection element, we mean important areas on the bridge that are significant from the standpoint of inspection check, that you have to cover those points. That's called inspection element. And then you need to fly this drone along this path autonomously without human intervention, even in areas where the GPS signal is not available. That's the big if, right? When the GPS signal is not available, the drone is still able to fly autonomously. And finally, from time to time, the drone has to stop at these inspection elements and take high-quality picture of these inspection elements. And finally, you need to analyze the images captured by the drone to identify defects and classify them into their corresponding categories, right? So that's the things that you need to do. So all these steps currently are mostly done manually, and we want to automate them away. So that's what we want to do. So how do we create the 3D model? Given a target bridge segment that you want to inspect, first we take a set of pictures at that bridge segment at a well-defined angle and well-defined distance to create something we call a rough 3D model. And then that's the magic comes in. Based on this rough 3D model, we use this rough 3D model as a baseline and contiguously scan the bridge segment and apply the so-called structure from motion algorithm to create the detailed 3D model that we want. Once we have this detailed 3D model as shown here, we can use it for interactive browsing and for computing the inspection flight path. So how do we calculate this path? Given a target bridge segment and its detailed 3D model that I just described, we first select a large number of waypoint candidates surrounding that target bridge segment. And for each waypoint candidate, we apply a so-called visibility calculation algorithm that computes the coverage of the bridge from the standpoint of that waypoint candidate. And then based on this visibility calculation result, we filter and select a subset of these waypoint candidates to form the final inspection flight path. Now, the resulting inspection flight path has the following property, that waypoints on this path are guaranteed to cover each and every inspection element, which again, important areas of the target bridge that we need to inspect. It can cover each and every inspection element at least a certain number of times. So it guarantees to cover all the important inspection elements. This is something that existing drone-based bridge inspection system cannot do, right? So now we have this inspection flight path that I just calculated. We just need to fly the drone along the path. Nowadays, this is not an issue. This is not a problem anymore, that a lot of systems can fly a drone autonomously without human intervention along a predefined path. But we need to do this until even when the drone is flying under the bridge, where the GPS signal is not available. So why is this important? When a drone flies, it needs a positioning information of itself, which is typically provided by the GPS signal. So when a GPS signal is not available, it doesn't have this position information anymore, and therefore it cannot fly properly. To address this problem, we use a so-called visual SLAM algorithm that can compute dynamically the drone's position and therefore enable the drone to fly under the bridge, even when the GPS signal is not available, right? So how does this visual SLAM algorithm work? It is shown on the left. So when a drone flies under the bridge, its camera is facing upwards, so it's seeing something upwards, and returns a continuous sequence of images. This visual SLAM algorithm is going to analyze this sequence of images and compute the drone's position by capturing the similar points on consecutive video frame, and then you can calculate the drone's position. The same visual SLAM algorithm can also enable a drone to fly in an indoor environment where, by definition, the GPS signal is not available, as shown on the right. So it can now fly smoothly and based on the planned path without any problems. So the next step, now we can fly the drone along the path. But we want the drone to fly in the following way. We want the drone to fly faster So that you won't just look at everything very carefully, but it's very slow. We want it to fly faster when there's nothing going on. And we want it to slow down and pay attention when there's something going on. So that means that the drone needs to have a capability to feel that there's some sign of trouble or some sign of defects as it flies along the path, as shown on the left. Like usually it just flies at a high speed. And then from time to time, it will stop and take a look at it if there's something interesting. And after that, it picks up the speed and move on. That's the desirable behavior that we want. All right. Now, when the drone flies along the path and it reaches an inspection element, so remember I say inspection element is the part of the bridge that's important from an inspection check's point of view. In this case, the screw area on the frame of the bridge is an inspection element. That's something we care. This is another example. This is so-called support pad on the pier of the bridge. This is also an inspection element. As the drone flies, encounters such inspection element, it just stops and carefully takes a picture at them by taking picture from a proper distance, at a proper angle, and with the right focus. Therefore, the quality of the resulting picture can meet the formal inspection requirement. So you need to make sure the quality of the picture is high enough to meet this formal inspection requirement. And the last step is that once you get all these images from the drone, BITS uses an AI algorithm. This is what AI is good at, analyze things. So BITS just use a pretty standard sort of DNN-based AI algorithms to analyze these images coming from the drone and detect possible defects, classify them into their corresponding categories, put together the analysis result, and generate the inspection report. So once BITS can automate all of the above steps, the rest is very easy. All a bridge inspection operator needs to do now is to specify the bridge segment that he intends to perform an inspection check on, like on the left, and gets the process rolling, and the BITS system would take care of the rest. He can actually monitor the progress of the BITS system a little bit if he chooses to, but he can do this from his desktop or laptop computer by viewing the real-time video feed coming from the drone as shown in the right. So that's what you are going to see, how the BITS system is doing. So what's the upshot? The upshot is that BITS uses this end-to-end automation capability to cut down the bridge inspection cost by half and reduce the elapsed time to 1/3. The degree of automation of existing drone-based bridge inspection system can be classified into 4 levels, if you wish. So level 1, zero automation. Everything is done manually. That's almost like today. Most, if not all of the drone-based inspection system work like this. Level 2 automates the steps of computing the inspection flight path and flying drone along the path. So it automates these 2 tasks. Level 3 is level 2 plus the automation of taking high-quality pictures of the inspection element so that the resulting picture's quality meet formal requirement. Level 4, the level 3 plus the automation of analyzing these captured images and generation of the inspection report. So it used to be the case that a bridge inspection operator needs to be intimately involved in the monitoring and control of a drone-based bridge inspection process. The guy is very nervous whether there's something going on and whether everything works just right. So he has to stare at the screen all the time. So that's what's happening there. All right. But with BITS correspond to level 4 automation. We automate almost everything. All right. This is no longer the case. The same guy, the same operator, just needs to specify the bridge segment to be inspected and hit the start button. And then he can sit back, sip his coffee, and wait for the result to come back. Now the gap between these two operating modes reflect the enormous productivity gain enabled by the end-to-end automation capability of the bit system. So that's why it's so interesting, all right? Finally, I'm going to talk about a system called COTA, which is designed to automate the stress testing and the stress testing of an ADAS system and its subsequent enhancement based on the test system. I'll explain what these terms means just in a minute, all right? So what is ADAS? ADAS stands for Advanced Driver Assistance System, ADAS. So it's a form of autonomous driving technology, all right? Now, which actually encounters some bumps in recent months. For example, the permit of GM's Cruise to operate its robot taxis in San Francisco was pulled. Google's Waymo recently issued its first ever recall because some of its robot taxis collided with some pickup truck. But there was good news too. Waymo was given the permission to operate its robot taxis on high-speed roads in Phoenix, Arizona. So the lessons from all these developments are the following. First, level 2A+, level 2 ADAS is still the sweet spot that every major car manufacturer is still focusing on, level 2 ADAS. So that's one. Second, the main challenge of developing a robust ADAS product is how to comprehensively and cost-effectively stress test the exception handling capability of the ADAS system's core engine. Is how you do this test. That's the name of the game. So how do we do this stress test? Ideally, the simple answer is to be able to generate millions and millions corner test cases, like really weird test cases that can expose the weakness of the ADAS system under test. That's really the name of the game. So imagine that we have an ADAS system at hand, like this. And let's assume it's an open pilot, which is an open source ADAS software. So there's actually open source ADAS software. That's actually pretty high quality, all right? And then we have two things called vehicle dynamic simulator that simulates the vehicle that is under the control of this ADAS system. So you need a simulator for the vehicle. And you need a virtual environment simulator, which simulates the virtual world in which this ADAS system is supposed to operate in, right? Everything is done virtually in a computer. So you need something like this. So then, given this, what is COTA? COTA is the test case generator that supposedly generate these millions and millions of corner test cases and then play them in the virtual environment simulator. That's what COTA is supposed to be, generate these test cases. But it does more. It can actually, based on the test result and runtime log, to provide the following three types of feedback for each test case exercised against the ADAS system under test. First, it can tell whether that ADAS system passes or fails a test. So that's easy. Like when you take an exam, your professor tells you you pass or you fail. Well, that's what it means. Second, if the ADAS system fails a test, it can tell you which part of the ADAS system, the perception engine or the control engine, that's responsible for the failure. So it's like when you take an exam, the professor can tell you that this part of the material you are not very familiar, that's why you fail, okay? And the third feedback is that if the ADAS system fails a test, it provides a remedy to help the ADAS system to get better and eventually pass the test. That's the thing that we really want, right? The reason you want to take a test is you want to know where your weakness is. The reason you want to know your weaknesses is you want to get rid of it. You don't just want to know the weakness without getting rid of it. And that's what COTA eventually is designed to do. So I'm going to describe that just in a bit. So, in order to explain this concept, let's take a specific ADAS functionality called adaptive cruise control, ACC, as an example. In ACC, you have at least two cars. The the ego car, which is under the control of the ADAS system, is supposed to catch up with the car preceding it, the leading car, right? And until the distance between the two is reduced to a certain value. And after that, it tries to maintain this distance regardless of the speed of the leading car. That is, if the leading car speeds up, then the ego car should speed up. If the leading car slows down, then the ego car should slow down, okay? So that's how ACC works. Now, imagine you are an ADAS testing engineer, and you are supposed to generate a test script for ACC. That's your job. So first, you have to use COTA's editor to specify what we call logical scenario for that test script. In that logical scenario, it's going to describe the set of vehicles involved in the test. In this case, minimally 2 cars, the ego car and the leading car. And then you would describe maybe the initial distance between the two, maybe the speed profile of the leading car, and so on. So that's what you specify first as a logical scenario. In addition, you specify the road environment, the road on which these vehicles are going to run on, right? Whether, how many lanes does this road have? Whether this road is straight or curved, and what's the degree of curve? Whether there's a turn, whether there's an intersection, and the intersection is a T section, Y section, roundabout, and so on, right? That's a road environment you have to specify. Now, this is where COTA does its magic. By enumerating all possible valid combinations of the parameters associated with the logical scenario, the road environment, the weather condition, the times of day, and the lighting effects. It's going to generate all possible legal valid combination, right? So each resulting combination now corresponds to a test case, okay? So that's how you generate this test case. So this slide shows, Let's go back, go back. And forward. So this slide shows sort of multiple example test cases generated from the same logical scenario and road environment. But we vary the times of day, the weather condition, the lighting effects, and so on. As you can imagine, there's a lot of parameters you can vary. So if you have like a 20 parameter, each parameter have like 5 possibilities, then you do the math. There will be a large number of variation or combination that you can produce. So now, once we generate, COTA generates these test cases, it's going to exercise each test case against the ADAS system under test, right? So this is the first case. It's a simple case. It corresponds to a noontime on a clear day, all right? So the visibility is good. And the ADAS system under test does what ACC is supposed to do. It tries to catch up with a leading car, and when the distance is at a particular distance, it maintains that distance throughout. So it passes the test. Along the way, COTA also provides some detailed execution statistics so that we can analyze what's going on. For example, it provides something called error in the distance estimate between the ego car and the leading car. So there's a distance, and the ADAS system is estimate that distance. And because we know the ground truth, so we can show the error between the ADAS system's estimate and the ground truth. So that's that error. And then it also shows the time and the extent to which the brake was pressed. When was the brake pressed, and how hard it was pressed is also shown in the third figure. All right, so that's what COTA can provide. And with that, we can analyze the second case. It's also a noontime, but on a heavy, foggy day, a lot of fog. So the visibility is very poor. But the same logical scenario. As you can see, the ego car eventually ran into the leading car because the visibility is very poor. So by the time it detects the leading car, it's too late. It's too late. And therefore, it fails the test. Now, if you examine the error plot, it seems like the error of the distance estimate is much higher than the previous case. That's the reason, because there's a lot of error in estimating the distance. And also, as a result, the brake was pressed too little, too late, and leading to the eventual unavoidable collision. And therefore, it fails the test. So now we know the reason, all right? Now, in the next case, it's also a clear day. The visibility is also good. But for some reason, the Eagle car cannot recognize an obstacle lying in the middle of the road and eventually ran into it and therefore fails this test, right? So turns out that this obstacle is an overturned truck that lies sideways across multiple lanes. So this is a very unusual scenery for a ADAS system. And the perception engine of the ADAS system cannot recognize this overturned truck. Why? Because it was never trained with images of this kind of object during its development. It never sees anything like this. Then, of course, it cannot recognize this. Now, knowing that this is the root cause, that the perception engine of the ADAS system is the system, the subpart that's responsible for the failure, and the reason it fails is because it cannot recognize this kind of object, COTA says that maybe we can generate additional test cases similar to this one, but contains a lot of these overturned trucks. For example, like this. So the first one, you show that immediately there will be an overturned truck, but lying in a different direction. And this one, then you will see an overturned truck on the side. And then this one. So when you drive, you don't see anything, but when you make a turn, you see another overturned truck. Now, COTA generates these additional test cases and then uses these additional test cases to retrain the perception engine of the ADAS system. Once this retraining is done, it then applies, it then retests this retrained ADAS system with the same test that it previously fails. And this is what happens. So, of course, sure enough, this retrained ADAS system is able to successfully recognize the overturned truck and stops properly without colliding with it, and therefore eventually passes the test. Remember what I say, the reason you take a test is because you want to know your weakness. The reason you want to know your weakness is because you want to get rid of it. So COTA not only can expose your weaknesses, we can also help you to correct that weaknesses. That's why COTA is so unique. So what's the big deal of COTA, you might ask? So we started the development of COTA with the aim to generate as many corner test cases as possible to stress test an ADAS system. That was what it is set out to do. What we set out to do is something like this. But later on, we figured out that we can actually do much more. We can actually do much more. By carefully analyzing the detailed log of the execution of a failed test, COTA can actually learn a lot. In particular, it can pinpoint the specific deficiency in the ADAS system under test of why it fails that test, and the part of the test case that exposes this deficiency. Two things. Which part of the ADAS system that causes this failure? Second, which part of the test case that exposes this deficiency, right? So now it can do. Now, armed with this knowledge, COTA is able to generate additional test cases that can be used as remedial training material to help the ADAS system under test to correct the corresponding deficiency and get better, right? So in other words, whenever COTA is able to successfully generate a test case that the ADAS system fails, it can identify the deficiency responsible for the failure, and it can provide a remedy to correct or remove the deficiency, and then repeat the loop. I claim that it is the COTA's capability to completing this test, identify problem, remove problem, test, identify problem, remove problem loop that uniquely pushes beyond the state of the art in ADAS testing. That is, to our knowledge, there's no other ADAS testing can do anything like this, okay? So eventually, under quota, when ADAS system fails, the more tests ADAS system fails, the better it is going to get. This is somewhat sort of like a paradox, but that's what happens. Like the more tests you can fail under quota, the better you are going to get, all right? So finally, we all know that AI technology is eating the world, and the revolution is just beginning. Delta has been a major player in development of efficient power delivery and thermal management solution for the emerging AI computing infrastructure. This is well known. But it also contributes to the AI revolution in other ways by developing innovative AI solutions for various other applications. So today I talk about 3 such AI solutions. The first one extends Wi-Fi from a communication technology to a powerful and versatile sensor. The second one enables end-to-end automation of the drone-based bridge inspection system. The same technology can also be applied, as we do now, to solar panel farms as well as wind power turbines. We can also do inspection for that kind of things. The third solution automates the stress testing of an ADAS system to expose its weaknesses and then systematically eliminating those weaknesses. There are still other AI solutions in the work right now. For example, we have autonomous mobile robot that can ride legacy elevator. Like you can take elevators up and down without human intervention. And we have an AI-driven PCB layout tool that is specifically tailored to power electronics circuit design, and so on, and a bunch of other things. So I don't have time to talk about. So what does this leave us? Like, in the era of AI revolution, people tend to think that Taiwan can only play in the hardware space. That's what you have seen in almost like all the talks in COMPUTEX. Now I claim, now you can honestly tell them that this is just not the case anymore by pointing to the kinds of AI solutions that I presented today. Thank you very much for your attention.
AI